Hello, thank you so much for watching this video, Onboarding Robots in Teams, a model of human-robot team cognition. My name is David Schillinger, and I am a graduate student of industrial organizational psychology at Penn State University. And this project is in collaboration with Dr. Susan Mohammed, also of Penn State, as well as Sydney Begerowski, Katelyn Hedrick, Jordan Smith, and Dr. Marissa Shuffler, all of Clemson University. So from the potential of introducing self-driving cars to roadways to autonomous manufacturing technologies that are already being used, it's clear that robots are changing the nature of work as they're being implemented into more and more work contexts. Now, on the one hand, robots do have a lot of potential to add value to work by handling tedious or physically dangerous tasks, or by increasing work efficiency by working on off hours, like on the weekends or at night. However, with the introduction of new technologies comes the risk of compromised communications, especially in complex, dynamic, and interdependent work teams. And so, in order to successfully integrate robots onto work teams, it's important that human team members not only be on the same page about sequencing and coordination, but also about robot capabilities and limitations. The team cognition literature so far has assumed human-human teaming in much of its work and has not really integrated robots or much technology. On the other hand, the human-robot interaction literature has focused largely on human-robot dyads performing fairly simplistic tasks and therefore has not fully integrated teams working in complex systems into their models. So overall, not much is really known about how to successfully onboard robots into teams in order to best facilitate team members having shared, accurate, and dynamically updating understandings of robot capabilities. Therefore, the purpose of this project is to integrate team cognition and human-robot interaction literatures in order to create a model of team cognition for human-robot teams. Now, it's important that we lay out some of our definitions and boundary conditions because, especially when defining robots, as well as team cognition, there are a lot of different definitions out there. So for the purposes of this model, we are defining robots as embodied agents with physical features roughly resembling human characteristics. And what we mean by agents is that we distinguish them particularly from technology because agents fulfill a role on a team by making a unique contribution rather than simply making humans more effective as technology would. We define team cognition as the knowledge building processes or the emergent mental representations characterizing the degree of convergence of team-related knowledge, content, and structure. And an important boundary condition that we're considering is that the robot is working interdependently with human team members rather than independently from them. There are three main elements of team cognition that we will be examining in this model. First is team cognition accuracy, and that depends on members being correct about robot capabilities. This question here incorporates literature on transactive memory systems. Next, we're considering sharedness, which requires that members be on the same page about various elements of how the robot is integrated into their teamwork, task work, and time work. And this question incorporates team mental models. And lastly, updating is looking at how human team members must update their team cognition regarding changes in work contexts that involve the robot, incorporating the team situation awareness literature. So, overall, when considering team cognition accuracy, if members overestimate what a robot is capable of, that might result in improper or even dangerous use of the robot. However, underestimating the robot might lead to underutilizing the robot and compromising efficiency. Considering team cognition sharedness, a key element of consideration is how the robot is pushing or providing information to humans, as well as trying to pull information from them so that both the humans and the robots can work together smoothly. Further, it's important for members to all have a shared understanding of how, when, and where that robot fits into the team's action and information flow. And finally, when considering team cognition updating, it's really important that human team members have a clear understanding of a robot's intent behind its actions, so that they can better adapt to changing situations or changing behaviors in the robot. If they understand why the robot is behaving how it is, then they can be more effectively reactive to its behavior. So next, we're considering several important contextual factors in this model. The first is levels of automation. Robots can vary in the extent to which they require a human operator, from complete operator control to fully autonomous. In practice, full autonomy doesn't really exist, and there's a little bit of debate about whether we even want that to exist. But in large part, most robots lie somewhere in the middle of that scale, requiring some level of human input as well as operating under some level of autonomy. Higher levels of robot autonomy may present a greater risk for reduced situation awareness, however, when human team members can walk away from the robot and leave it to do its own thing without much oversight, thus reducing how much they're aware of what's going on with the robot. However, on the other side, when we're looking at lower levels of automation, that can increase the risk of workload for the human team members, because it requires those team members to babysit the robot more while they're also trying to attend to their other work responsibilities. Next, the amount of time that the team has spent with the robot is an important contextual factor to consider. Early on in a process, when the robot is first onboarded, there might be a significant lack of trust toward the robot because the humans are unfamiliar with this new piece of technology and how it might operate. Over time, if the robot is performing well, then the team might get a lot more comfortable and increase its trust directed toward the robot. However, if a robot spends several months working with team members, but that robot is failing or making errors a lot, that's likely going to lead to a lot of distrust among those team members as the relationship grows in time. And finally, the number of human operators managing the robot is important to consider. Because of its implications for how knowledge about the robot's operation is distributed across human team members. So for example, if there's one human operator, it might be a little bit easier for the rest of the team to understand if there's something we need to know about the robot, that's the person to go to. If there are several operators, if they all do the same thing, maybe that might be a little bit easier because there are more points of contact. But if there are multiple operators who all have different levels of expertise or expertise in different elements of the robot, that requires a little bit more work in managing transactive memory systems among the other team members to understand who they need to go to when managing this robot. So overall, here is our conceptual model for team cognition for human-robot teams. It includes 3 elements of contextual influences on the top, exploring robot level of automation, team tenure with the robot, as well as the number of robot operators. Next, we look at mental model accuracy, which asks, are team members correct about robot capabilities? Moving on to mental model updating, asking, are team members adapting to the changing situation regarding the robot? And finally, mental model sharedness, are team members on the same page about the robot? We expect that these 3 facets of team cognition are going to impact a number of important outcomes, such as team performance, especially team performance under failure conditions where the robot malfunctions, underestimating or overestimating robot capabilities, as well as developing trust in the robot's capabilities. Overall, in response to the growing occurrence of human-robot teaming, we here have derived a model for team cognition for human-robot collaboration that addresses accuracy, sharedness, and updating of mental models about robots. And in doing so, we have also integrated several bodies of literature on team cognition, as well as human-robot interaction. We hope that this can spark future research opportunities into the challenges of introducing robots into complex, dynamic, and interdependent team contexts, as well as the benefits that that might provide. So thank you very much for your attention to this presentation. We're all very enthusiastic about this project. Again, my name is David Schillinger. You can feel free to contact me at djs6947@psu.edu. And I'd like to, again, extend a thank you to the rest of our team. I appreciate everybody's time and dedication to this. Without your knowledge and willingness, this would not have come together. So thank you very much.